In order to integrate a complicated function, I really just want to antidifferentiate complicated functions.
For example, can I antidifferentiate x times sine of x squared dx?
And if you think back to when we were doing all our differentiation stuff, a big deal was the chain rule. We were always using the chain rule in order to differentiate things.
So for this problem, I might try to think in terms of the chain rule, right? I know some function whose derivative is sine. Minus cosine differentiates to sine. But then I want an x squared in there somehow, so I'll put an x squared there and I'll see, is that an antiderivative of this? Well, let's try. So if I differentiate this, what do I get? Well, the derivative of the outside function is sine, evaluated at the inside function, times the derivative of the inside function, which in this case is 2x. And then I see, whoops, I'm off, right? I didn't quite get an antiderivative. I'm off by this factor of 2, so I can fix that. I'll just divide this by 2, which will have the effect of dividing that by 2, but then these 2's will cancel, and now I have found an antiderivative for x times sine of x squared.
And yeah, that works, but it was totally ad hoc. I mean, how did I know to divide by 2? I just guessed and then fixed my guess. Mathematics really shouldn't be seen as just a series of tricks. A big part of mathematics is systematizing those tricks, finding the patterns that unify a trick into a tool. In this case, we really want to systematize applying the chain rule in reverse.
So this process of applying the chain rule in reverse goes by the name U substitution.
It's also just called substitution, but I'm going to call it U substitution to emphasize the conventional name U that I'm going to use for the inside function when we're running the chain rule backwards. This is anyhow all too abstract. Let's just see this in action.
So I'm trying to antidifferentiate x times sine of x squared dx. And the trick here is to give a name to the inside function in the chain rule. I'm going to call that U. And I want the inside function to be x squared. So I'll say that u is x squared. Well then what's du, right? What's the differential of u? Well, du over dx is the derivative, which is 2x. So du is 2x dx. And now you might feel kind of bad because, well, I don't really see a 2x dx. I only see an x dx. But this sort of method kind of guides us to do the right thing. I'd like to have a 2x dx, so I could put a 2 here as long as I'm willing to put a 1/2 on the outside. It's like doing nothing. But now I've got a 2x dx in the integrand, and that'll become my du. So this antidifferentiation problem is the same as sine u du, and I've got to make sure to include that 1/2 on the outside. But now I know an antiderivative for sine of u, right, is negative cosine. So I've got 1/2, and then an antiderivative of sine of u is negative cosine plus c. But I don't want my answer to be in terms of u, so I'll rewrite this as negative 1/2 cosine of u, which is x squared, plus c.
There's something to notice here. I'm using differentials with the chain rule, so that dx is playing a crucial role. You might have thought that I was just writing dx at the end of my integration problems, just out of habit or tradition. But that dx is legitimately there. That dx is managing the substitutions for us. Let's see why this works.
Well, every differentiation rule has a corresponding anti-differentiation rule, right? Let's say that I want to anti-differentiate f prime of g of x times g prime of x. Well, secretly, I can recognize this as the derivative of f of g of x with respect to x. But let's suppose that I start writing it down using this substitution framework. So I'll make a substitution. U is g of x, and in that case, du is the derivative of g dx. So this antidifferentiation problem is the antidifferentiation problem f prime of u, and this is now du. But I know an antiderivative of a derivative. It's just the original function. And in this case, u is g of x, so this is f of g of x. And of course, I can really see this working. You know, the derivative of this composition is this. It's just the chain rule.
we're going to see a ton more examples of this technique. And we're going to see that the hard part boils down to determining what to set u equal to. But if you're ever wondering why does u substitution work, remember it's just Ilor-Nyack.
I mean, u substitution is Ilor-Nyack, chain rule, but just in reverse.